All right. So here's the deal. We know functions have power series expansions. Okay? And this might look like C0 plus C1 x minus a to the 1 plus C2 x minus a squared plus C3 x minus a cubed on and on. And up until now, we've sort of taken the tact that if we know what the power series expansion is of some function, we're feeling lucky. And then we can take that function and we can modify it or alter it. But really, we want to ultimately turn that around and say, hey, give me the function and you can give me the power series expansion. Okay, you won't be able to do that with any function. And the thing that's standing in our way is knowing what the coefficients are. That's the only thing standing in our way. So if we can come up with a way of finding out what those coefficients are, we'd be good. This is a power series approximation, and we call it centered at A. Remember, we use that terminology. So, and you can think about this. Power series approximation is probably going to will do one of three things. So if you have some function, the power series approximation might only approximate the function at one point, when x equals a. Okay? Or maybe it does this.
It's always centered at A?
It's always centered at A. So whatever A is, that's going to be the center. And if it's going to be a good it will always be a good approximation, at least at A, because they share that point. Maybe your power series approximation hangs out and does it for an interval. Or maybe the more terms you use, the power series approximation, the power series expansion fits that function perfectly. Go ahead.
Is that A the same as from x minus A?
Yeah, right? Okay, so back to this. If only we knew the coefficients. So you were asking this question the other day, whether you know it or not, right? You were saying, well, what if I wanted it somewhere else, like not at 1, or not at 0? Well, I'm going to play a little game. You don't have to, all you need to do is check to make sure what I'm doing you agree with, and I promise I'll summarize it in the box. Right? But right now I just need you to play the game a little bit. Okay, so first things first. F of x is equal to this whole thing. I think I'll maybe stop at the 4th term, knowing that I can keep going on. Okay, I'm going to let x equal a. You don't have to write this down. You can if you want, but you really don't have to. I promise I'm going to summarize it very nicely. So if I let x equal a, what's the right-hand side become? F of a. Did I say right hand? Sorry, left hand. What's the right-hand side become?
C1 and then, oh no, just 0. It'd be 0 on. Nah, just C0.
Okay.
Yeah.
So, tell you what, I just found out what the coefficient C of 0 is. This coefficient is f of a. Okay, so I found you a coefficient. That's nice. All right, I'm going to erase this because it's not really that important right now. All right, now remember we talked about being able to take a series and do term-by-term differentiation? That's what I'm going to do. What's the derivative of C0?
0.
What's the derivative of C1x minus a to the first?
C1.
Is that okay?
No, wait.
X. No.
Is it?
Yes. Just
No, I thought it'd be C0x.
No, the derivative of C0 is 0.
Oh, I
that's
see, I
nothing.
see.
That's 0.
okay,
So
C1 minus. Yeah, it's just C1.
x
C-
minus a
C1x.
raised to the x minus 1 raised to the
1.
0.
0. Anything to the 0 is
1.
1. Okay, C1.
Yeah.
Okay. The derivative of this term?
C2 times x minus a.
Sorry about that. Raised to the
Just
first. Okay.
3c3 times x minus a squared.
Whoops. That's not x to the 4th. Right, that's, oh boy. What happened there? X to the 3rd. Oh. Okay, so I'm going to do the same thing. Let x equal a. What do I get?
Same thing. C1.
C1 f prime of a equals C1. Hey, I just found you the second coefficient.
Oh,
C1 is the derivative of a. Alright, so if you give me a function, I'll tell you what the coefficient. The first coefficient is f of a, whatever that function is. The second coefficient is f prime of a.
take the derivative in infinite times if I'm
All right.
over
I don't know if I have an infinite number of times in me, Alina, but I have a few more times in me because I think we're going to start to see a pattern. Alright, term by term differentiation. Derivative of C1, derivative of 2C2. Sorry, 2C2x to the negative x minus a. So just 2C2.
Yeah. 6C3.
Alright, I'm going to leave it as 3 times 2, C3 times x minus a, plus 4 times 3, x minus a squared. I did. You're right. Thank you. Okay. Guess what I'm going to let x equal? Let a, yeah, what am I going to let x equal?
A.
A. What drops out? Right, all of this drops out. For those of you watching, you know, when you're going back to look at this, all that drops out. And I'm left with the second derivative at a, because x is equal to a, equals 2c2. What's c2 equal to? Second derivative of a over 2. Just a guess? You want to guess what?
The third derivative of a over 3.
Alright, so is it going to be over 3 or is it going to be over...
Oh, yes.
So it'd be nice if it was like over 1, over 2, over 3. But that's not quite how it works out. If we take the third derivative, we're going to get 3 times 2 times c3 plus 4 times 3 times 2. Whoops, I keep forgetting that c4, Emily. c4 x minus a. So if I let x equal a, everything's going to drop out. So if x equals a, I get the third derivative 0 equals 6c3, or c3 equals third derivative at a over 6. But if I wanted to be, I'd probably write 3 factorial. And I'd probably write 2 factorial. And I'd probably write 1 factorial. And I'd probably write 0 factorial. 0 factorial is defined as 1. Yep. And that's very convenient, right? Very convenient. So I have a pattern for the nth coefficient. Okay, it seems to me that the nth coefficient is the nth derivative at a divided by n factorial. And I have a special notation, and then I'll put up the PowerPoint slide that has it, but I would say this, for a power series, the nth coefficient is equal to the nth derivative at a, and that's how we use the notation for nth derivative. So for the third derivative, you can use 3 little, like, prime marks. But if you were talking about the eighth derivative, it'd be really hard. It'd just be annoying to do, you know, prime, 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 prime. So the eighth derivative would be f superscript parentheses 8 of a. That means the eighth derivative. Okay. I think we may have seen that notation like a long time ago. And now I'm ready to put it in a box. All right. Whoops, thinks my finger is some sort of marker. Nope, don't even think about it. Ah. Water fine, colored water with caramel added, not so fine. All right. Here we go. So, if a function has a power series representation or a power series expansion, okay, so if it takes on this form, and there's some radius of convergence, we haven't talked about that. If there's some radius of convergence, then each term, each coefficient is going to be equal to the nth derivative of the function at a over n factorial. And that's something you need to know, you need to memorize, you need to be able to compute without your book or without a calculator or something like that. Okay? And we're going to do an example in just a second. All right, now we have two sort of special power series that we're going to talk about, and I don't know that it's I mean, if you feel compelled to write down the special power series, you can. I need you to let you know that they're in your book. Right, so I'm not trying to hide any secrets from you. All right, so we call this is a power series. And not only that, this is a power series where I'm telling you what the coefficients are. This is a very special power series called a Taylor series. So a Taylor series is a power series representation of some function. And not only that, I'm not just saying it's any old power series, I'm saying it's a power series where I can tell you exactly what the coefficients are based on the derivative of the function and where we're trying to approximate, right? So this is your idea. Am I trying to approximate at x equals 12, at x equals 0, at x equals 1, x minus a. A is where a is the center of the approximation. You okay? You don't seem as excited as you could be. Now, this becomes a simpler formula if it's centered at 0. Right? If the center is 0, instead of x minus a, it's just x squared, x cubed. And that is a very special type of Taylor series. That's called a Maclaurin series. Right? So, a Maclaurin series is a type of Taylor series. A Taylor series is a type of power series. You can call a Maclaurin series, you can call it a power series, you can call it a Taylor series. Sort of like this is the square of quadrilaterals, right? You can call it a rectangle, you can call it a rhombus, you can call it a parallelogram. So a Maclaurin series is a very, very specific type of Taylor series, which is a specific type of power series. And we're going to do some work, because we need to get practice doing this. And I think if we do one together, then we'll be in good shape to ask questions about what we did, and then I'm probably going to have you do a couple on your own. You ready? Carly, you ready?
I'm ready.
All right, so here's the one we're going to do together. We're going to take a look at, for f of x equals ln of x, we're going to find the Taylor series So, as soon as I hear Taylor series, I know this. I know ln of x equals something plus c sub 1 times x minus, now where are we centered?
1.
1. So it's going to be x minus 1 to the first. Plus c2 x minus 1 squared plus c3 x minus 1 to the third. On and on. Okay. So my goal is to find what those constants are. Well, I have a pattern. I have a rule. Go ahead.
Oh, how do we know that it's centered around 1? I'm a little bit...
That's what we asked. Now, you don't have to. You can ask a different question if you'd like. You can say, hey, maybe I want a Maclaurin series. Maybe I want to center it at 0. Okay. But in this case, you have to specify where you want your series centered. Okay? All right, so I know that C0 is equal to f of
1. Or
1.
1 of 1. Which is
f of
0.
1, which is the natural log of 1, which is equal to 0. So I know my first term 0. Why? Because I have memorized what the coefficients are. The coefficients are f, the nth derivative of f at the point over n factorial. So the 0th term coefficient is the 0th derivative, which is f of 1 divided by 0 factorial. All right, that's great. Let's see, what does it think my finger is? Let's make it an eraser. Okay, so that's 0. Now, the first coefficient is f prime at 1 over 1 factorial. So I have to be able to take the first derivative of the function. First derivative of ln of x?
1 over x.
1 over x. So in this case, it's going to be 1 over 1 factorial, which is equal to
1.
1. All right. So I have my first two coefficients. Second coefficient, the rule says, hey, that's the second derivative at 1 over 2 factorial. All right, I need the second derivative. And maybe I probably should have said, hey, the first derivative is 1 over x. What's the second derivative? What's the derivative of 1 over x?
So you have negative 1 x, negative 1 over x squared.
Negative 1 over x squared, all divided by 2 factorial. And when x equals 1, that's going to be equal to negative 1 half.
Negative 2x cubed, negative 2 over x cubed.
All right, let me catch up. Just note, I just want to note, it's a little hard to guess what the pattern is now, but maybe after doing one more, we'll see like what the pattern is. So, the third derivative 1 over 3 factorial. So, Greg, you told me the third derivative is
Negative 2 over x cubed.
negative 2 over
I
x
thought
cubed.
positive 2 over x cubed.
What do you say?
Yeah, positive, I'm sorry.
Positive. All right. Positive 2 over x cubed all over 3 factorial. So what's that? 2 over 6.
2/3. Yeah.
So 1/3. So are you ready to maybe make a guess?
Is the next one going to be negative 1/4?
Yep. Okay. Does that work? Does my summation notation work? It's 1 over n times x minus 1 to the n, where n starts at 1, not at 0. It starts at 1. So I get 1 over 1 times x minus 1 to the 1. Ooh, what am I missing?
The alternate negative.
I gotta
Yeah.
make it alternate.
Negative
Just
1 to
add
the
it.
n.
Yeah.
All right, so what do I need?
Add that in the final sum.
Negative 1 to the n plus 1. Is that what we have to do?
So if it's negative 1 to the n, that means my first term would be negative, but it's not 0. It's negative 1. So I can either do n plus 1 or n minus 1. I'll do n plus 1. All right, so I need to make it alternate. Okay, great.
That's an ugly equation.
All right, so I'm going to pause there. I want to show you the graph of this, and then I want to do even more, but it's a great place to stop. Are there any questions about the mechanics here? Would you agree that while there's a lot of work to do, the work's not hard?
I mean, yes, I agree.
Yeah, okay, the work's not hard, you just have to be willing to find derivatives, which is a great review. All right, so let's go back, and here I have ln of x.
Can you go back for one quick section? Just to,
I will in a minute.
okay.
Okay. I have ln of x, and I have this function x minus 1 minus 1/2, whoops, x minus 1 to the first, whoops, sorry, squared, plus 1/3 x minus 1 cubed. And if we take a look at the graph, there's the ln of x function, and then there's the polynomial approximation. Now, just looking at the graph, do you want to take a guess about the convergence of that polynomial approximation?
0 to 1.
So it's centered at 1,
Oh.
so maybe 0 to 2, maybe.
Okay.
Now, we actually, what we need to do, and I'm not going to do it right now, if we have time later I will, we would need to prove like what the interval of convergence is. Because we could do all that work only to find that our polynomial only approximates at x equals a. Or we could find that it approximates that it's equal to the function for all real numbers. So after you find the power series, or the Taylor series, or the Maclaurin series, you then need to ask yourself, great, when does this series converge on this function? All right, so now I'll go back.
And we just do ratio tests for that.
Yeah, 9 out of 10, more than 9 out of 10 times. 13 out of 14 times, the ratio test is the way to go. All right, this isn't where you want me to go back to. Hold on. Here? Here.
Yeah. And
All right.
that was my question.
All right. Questions, comments, concerns? I'm going to put you to work.
Do it.
All right, so let's have Alina, David, Greg. You're going to do the first bit of work. I would like, I'd like you all to find the Maclaurin series, so that's centered at 0, of sine x. Okay, so I'm going to say centered at x equals 0. Or I could simply say Maclaurin series. That implies centered at 0. Julian, Carly, and Emily, I'd like you to tackle cosine of x. Okay?
That's the harder one.
I'll give you like, I knew you could do it. I'll give you like 4 or 5 minutes. I wonder if there's a way to pause. I have a bad feeling if I hit stop, it actually stops.
Yeah, bro. Just talk to it.
Should I hum or something?
Yeah, sing a song or something.
La-di-da-da, la-di-da-da.
Play some jazz.
And give a message
we
to
need some
the
elevator music.
to these people watching the.
Make sure to do your homework.
Be good and kind, right?
Seniors, finish strong, be good and kind, stay out of trouble.
Lex said he was going to use his math book as a tray in the cafeteria.
Oh, that's terrible.
On the last
No,
day.
but your suggestion was for like first base or something, so we have to do that. We can't
Yeah.
I
disappoint.
used
No,
my
he
box
also,
to press
you know,
leaves
we were
in
going to
the
have him
fall
traded
time.
in for a home plate.
I'm going to take all them out before I return them. There might be a few in it, but I don't think that will disturb anybody who gets it.
Wax paper. Wax paper, both sides. That's good for pressing. All right, get to work. Come on. I already feel pretty good about the fact that sine x and cosine x, the derivatives are easy to find. And I'm also feeling like the derivatives, when I evaluate them at 0, some of them are going to be easy.
You mean sine of 1?
Hold on.
You can use the front of my binder. That's some stuff. Like the people watching the screencast might fast forward this part.
It would have been nice to tell them, like,
Yeah,
fast forward
oh, yeah.
to,
Yeah.
but we'll never know.
You're still watching, the answer's pi.
Oh, that would have been a good way to ask somebody to record that on one of your videos.
Yeah, to ask.
You'd have to know the person.
You have to be asking somebody in this class and somebody who
would
you'd
watch
be
the
like,
video.
and then you'd have to be like subtle about it, like, oh, you should totally check out the screencast. There's some great formulas in it.
Be good though. It worked.
So shocking. Did he take the derivative and go to prom?
Goodness, the limit does not exist.
I still like my idea of graphing it out, polar coordinates.
Alright, so what is this going to end up being? Because I got C of 0 is 0, C of 1 is 1, C of 2 is 0, C of 3 is negative 1/6.
Oh, I'm giving you a different answer than you.
How are you doing?
I'm doing it
What
right.
is it?
Wait, but if A is 0, right?
It's just sine.
A is 0. Then isn't C of 0 undefined?
Yeah. And? Derivative sine is
Oh wait, I get it. No wait, aren't these all undefined? Because
You don't have to do that. It's just a simple one-term convergence. Yeah, you get one.
So you're getting, are there some terms that are dropping out that are going to 0? Some
Yeah, there's so
like
every
other one
is 0.
goes to
Sine is
0? Okay.
So wait, it's just gonna repeat depending on.
I'm getting the odd number coefficients as 0. Is that wrong?
Even numbers coefficients should be zeros. So sine is the first one.
Sine of 0 is
Oh, yeah.
0.
0.
Yeah, we have the.
Okay. Cosine
Yeah.
of 0 is 1.
You
Cosine of
know their
negative
problem.
1's. Okay.
Oh, I was plugging 1 in for all of them. Yeah, and then you said specifically when you times that the center is 0. So that was really stupid.
So
Are you guys good? Sort of.
Is C1 part 4?
C1 is 1.
What?
I told you it was pi.
Oh yeah, it's what?
I don't think there's any
I'm
pi.
so confused.
There's no
From what I know, sine of 0 is 0, negative sine of 0 is 0, cosine of 0 is 1, negative cosine of 0 is negative 1. So there should be lots of zeros and lots of ones and lots of
Alright,
negative
this
ones.
is bizarre. So I'm going 0, 1, 0, negative 1/6, 0, 1, 1/20th. then it'll be 0 again.
You should definitely have x's in there,
Eh?
right?
That much.
The
Oh,
coefficients
that's very clear.
times x squared times x cubed.
Right. Well, it wouldn't matter because we're
Well,
plugging in
it's
0.
it's
Wait a minute.
Just the over.
So,
10 plus
I don't think I did this right. I feel like it should be much more convenient to
Zero
put
term,
together.
it's gonna be over 1.
maybe
You
not.
get like 0, 1/2, 0, negative
Then here,
124.
1, it's gonna be 2.
Something like this.
Right, boys.
Like that, but
hold
not
on,
like
listen
that.
up, listen up.
3, 4 factorial.
A is
This
0.
1 factorial.
X is x.
Yeah.
So it's 1/2 x,
This is the third term, the third term.
like 1/24 or 1/2
No,
x
we're talking
squared.
about each term for C.
Right. I still need you to like tell me that it's x minus 0 to the first, x minus 0 squared, x minus 0 to the fourth. Right. So there's still an x in there. You can't just tell me. So like, coefficients are great, but put it all
This is-
together.
But if the coefficient is 0, then it doesn't matter.
This is true. So some of the coefficients will be 0, but some of the coefficients won't. Times x.
Oh, what?
Oh, you mean we need
Right.
to plug it?
All right. I'm ready.
I'm
What do you guys have? Are you guys sine or cosine?
Where?
No.
Did your first term drop, or was your first term 1?
First terms.
1? Okay. Did your second term drop?
Yeah.
All right. Minus
1/2.
minus what?
1/2 extra.
1/2 x squared, or x squared over 2. All right. The cube term drop.
Oh.
Okay. The fourth term.
1 over 4 factorial.
All right. So plus
Yeah.
plus x to the fourth over
Oh, I see. So ours
4
is gonna look
factorial minus
X is 6 over 6 factorial.
x to the 6 over 6 factorial. Okay.
So ours is
Two
going to look like
factorial.
1 or x over 1 factorial,
Yep.
x cubed over 3 factorial, x to the 5th over 5 factorial, or something like that. That's what you're looking for.
Yep.
Yeah,
Okay.
I see
No,
that.
no, that's what you want. Just like, what?
Because we're looking for patterns, right?
Yes. Okay.
Okay, we're looking for
So I see it
patterns.
now.
Now, how do you feel about trying to put this in summation notation? Let's try. Do you want to do the evens or the odds? Let's try one.
Together.
You want to try to put this in summation notation?
Yeah.
So each time, what's it going to be over? So if this is the first term, the second term, the third term, or maybe I should call this the 0th term,
Yeah.
the first term.
We
All right.
got 2n factorial.
All right, so 2n quantity factorial in the denominator, and x raised to the 2n.
Yeah.
Does that work?
Then we need to alternate.
So we need to alternate it by doing -1 to the.
N plus 1.
Then it doesn't work. You plug in
-1 to the n.
2. Yeah.
So let's take a look. When n is 0, that's 1 times x to the 0 over 0 factorial. That's 1. When n is 1, that's -1 x squared over 2 factorial. Great, that works.
Wait. So, I'm following you for x over. I got something different. Did I? Here's my question. For this, is it c to 0? It's over 1 factorial, right?
Okay.
It's over 0 factorial.
Which isn't that
You just
undefined?
wrote anything down. No, I told you 0 factorial is equal to 1. I said that's by convention. 0 factorial is equal to 1. Okay? So, going back here, you don't have to have the last 3 memorized. Okay? But the first 4 you need to have memorized. So, it's in the book, yeah. So the first one's our friend the geometric series. Next one's e to the x, which we actually did a few weeks ago. Okay. There's the sine x, all right, which Alina, David, and Greg did. And here's cosine x, which Emily, Carly, and Julian did. Okay. Now, we actually haven't talked yet about the radius of convergence for any of these. Okay. David would probably tell us, hey, make sure to do something like the ratio test. I will tell you e to the x, sine x, cosine x, these series expansions converge for all real numbers, meaning that cosine of x is equal to this polynomial function so long as you add an infinite number of terms. And that's pretty powerful. A trig function, a trig function, cosine, is equal to a polynomial function. That's nuts. That's crazy. All right, questions, comments, or concerns? Because I have a little bit more to talk to you about.
So I still feel that. So I got c1 to equal 1. I got c to the 3 to equal negative 1 over 6 times x to the third. But there was something different written.
No, that's equal to
3 factorial.
over 6, Dave.
Yeah, that's over 6. I'm just writing it a different way.
And then the 1 is just not right. So x plus. Actually, that's the book wrote that.
So I think we have the same thing, just written.
Okay.
At least. I could be wrong, but I think.
No.
I think-
No.
Yeah. Okay. Thought you
I'm
had
sure
it.
you're right.
Okay. Questions, comments, concerns? Julian? Carly? Greg? All right. Backward is doing all right. Emily? Come on, this is sort of cool.
Yes.
Oh, yeah. David? I'm giving it an 8 count.
I'm fine.
All right, so one of the questions becomes, hey, this is great. How good is the approximation, or how good does it does this converge to sine x? And it depends on how many terms you use. So this is pretty interesting. Is that a good breeze or a bad breeze? It's a good breeze. All right. If you just use, I should say this. Okay, so if I take a look at sine x, let me go back and take a look at sine x.
After all this work, I'm not sure I feel like doing the ratio test.
Oh, we're not even done yet. Oh, that.
All right, so let's.
It's like, yay, it worked.
All right, so let's take a look here at sine x. I want to tell you that if we said that sine x is approximately x minus x cubed over 3 factorial, we would call x minus x cubed over 3 factorial a third degree approximation. Does that make sense?
Yeah.
Because it's the
The third degree.
because
Now,
technically you're-
I want to tell you about a little bit of ambiguity. And different books do different things. There's ambiguity over whether this is a 2-term approximation or whether it's a 4-term approximation.
Oh, because the c of 0 would be 0.
Right. So we have 2 terms that dropped out, right? So we actually calculated 4 terms, but there are only 2 terms that matter here. So I think there is some ambiguity, and I forget how your book treats it. Okay? If I'm ever asking, I'm going to ask for like a 3rd degree approximation. I'm not going to say, give me a 2-term approximation, thinking, trying to mess you up, not knowing, what does he mean, 2 non-zero terms or 2, 0, including the 0
What if the
terms?
first 2 cancel out?
Yeah. But this is interesting because actually what this says, if I want the 1st degree approximation, it says the sine of x equals x, approximately. And if you think about the graph, right, the graph of sine x looks like that. The graph of x looks like that, right? It's a decent 1st degree approximation. As a matter of fact, if someone says, hey, quick, what's the sine of 0.02? 0.02, right? You can sound super smart by doing those approximations in your head. Now, the further we get away from 0, the worse this approximation is. So if someone asks you for the sine of 1, do not say 1. Okay? The sine of 1 is not 1.
Say 0.
Arc sine. Sine of 1 is like the sine of 57 point some odd degrees in radians. So the sine of 1 is like, I don't know, root 3 over 2 or something. Yeah, something like that. But I can't do that in my head.
You were off by 0.02.
Yeah, check that out. Okay. Okay. And then the other question you might ask is, great, but how far off is my approximation if I use, one term or two terms or three terms or a fifth degree approximation. So we're not going to talk about it much today, but I'm just going to sort of foreshadow. If you use a seventh degree approximation for the sine function, your maximum error is the next non-zero term. So my error here at most could be
equal to the next term.
Right, and that should
non-zero, so
no, 9. And that should sound a little like the alternating series remainder.
Yes.
However,
The alternating series remainder.
however, this gets a little confusing because we're never going to, Julian, we're never going to ask you the question, how good is this approximation at the x value that we're centered on? We're never going to say, hey, how good is this approximation at 0? Because this approximation at 0 is perfect. It's perfect with a first degree approximation. Sine of 0 equals 0. We're going to ask, questions like, hey, how good is this approximation for this interval? And we're going to really have to think carefully about how this error will work. But the general gist, I'm just trying to lay the groundwork, the general gist is the error is at most going to be the maximum value of the next term. And I might have to think a little bit about what the maximum value of the next term means, depending on the question. Okay. So stretch your question.
It's a question.
Yeah, go ahead.
So those formulas, we have to memorize all of them? Or
Yeah, so if we go back to this.
these are in the book, I assume.
They are in the book. You're on the hook for these first 4. They're that important. Okay.
Oh, boy.
Now, I want to point out, like, the natural log of 1 plus, the natural log of 1 plus x, we actually talked about the function, well, we know 1, right, never mind. All right. We know.
Be able to see it.
I know, that's okay. We know that, right? And we said, well, if we know that, we know
That the derivative-
this, right? Which means we know this. And if you take the antiderivative of 1 over 1 plus x, you get the ln of 1 plus x, right? So you could actually get this from knowing this. The first 4, though, are the really, really important ones. And if you can know the first 4, then you can build lots of other approximations based on the first 4. Arctangent x actually comes from this. Instead of doing 1 plus x, we would do 1 over 1 plus x squared and take the antiderivative of 1 over 1 plus x squared. That's arctan.
It's just the same sign, just without the factorial.
Yeah. It is, right? And so and these patterns are all easy to sort of remember. This is called the binomial expansion. You might, depending on what you do next year, run across a professor that wants you to know the binomial expansion. We're not really going to be doing much. We're not going to be doing anything with binomial expansion. So, geometric, e to the x sine x cosine of x, they're all patterns that you can recognize, so they're easy to memorize. That's why we do them. And when you think about it, these are our fundamental transcendental functions. Is that like a bell?
Yeah.
All right.
It's not a shook bell this time.
No,
So
it's
we
not.
did think about it.
So I want to say this. Tonight's going to be a little hard, not because it's new, but if you remember, all you need to do is find the constants. You know how to find constants, right? So
What about
use your
questions
notes.
that fall?
Oh no!
Last night's homework, because I had a question on literally
Yeah, I
grade.
started class today with that. So I started saying, I know we're not going to get to questions from last night.
I really tried my best to be on time. I was coming all the way from downstairs. I'm like, oh,